Alright students, today we'll be looking at the final topic of our organic chemistry series on nitrogen compounds. So this will be the last topic which you need to review and study for your A-level exams related to organic chemistry. Yeah, so if you think back throughout your journey of organic chemistry, there's quite a bit of contents to cover. Yeah, so maybe I can just take a brief look at what we have so far. So if you recall, we started with introductory organic chem, right, where you learn about stuff such as isomerism, how to draw a stereochemical projection. You learn about chirality. Yeah, so that's on introductory organic chemistry. And if you also recall the little bit of things which you learn in that particular chapter, which could be a little bit confusing, right? You learn about the functional groups, the different functional groups, and if you record what was mentioned would be that once you encounter them later on in your organic chemistry journey, then there isn't really a need for you to memorize these functional groups. So I hoped that when we have reached the final topic on nitrogen compounds, you would have agreed with us on that. Okay, then at the same time, that particular chapter also introduced you to two very abstract concepts. That is the steric effects and the electronic effects when we are dealing with groups attached to a center of reactivity. Yeah, and I do believe that throughout the study of organic chemistry, we have given you numerous examples on how to deal with them. Yeah, I think you have heard me talking about it in chapters such as carboxylic acid derivatives, hydroxy compounds, carbonyls, etc. Yeah, so if you need to, please go and review them at your own leisure. And then after that, you are being introduced to alkanes, okay, which is the next topic, right? That is the hydrocarbon series, because after alkanes, you are being introduced alkenes and arenes, okay, before you break for your promotional exam last year. And these are the three organic chemistry topics which were being introduced to you in JC1. And of course, within these three organic chemistry topics, you were also taught the mechanism. So for alkanes, you learn about key mechanism associated with them, free radical substitution. Yeah, you learn about the unreactivity of alkenes, and that is why you need very reactive species such as a free radical to force a reaction out of alkanes. And then after that, you learn about alkenes. You learn about a reaction known as electrophilic addition. And the reason why is it electrophilic addition is because alkenes is electron rich with the pi electron cloud above and below the CC double bond, and they tend to be attracted to electrophiles. And then for arenes, you learn about electrophilic substitution. Okay, so for electrophilic substitution, you are aware that for arenes, in order to restore the aromaticity, it has to kick out a group, and that group is usually a H+, and in the process, reaction involve arenes somewhat replaces a H with a substituent, and that is why it's called electrophilic substitution rather than electrophilic addition. And your pi electron cloud in the aromatic compound or arenes, right, can attract electrophiles. Okay, yeah, so these are the three main hydrocarbon topics which you encounter. And then when you came over to JC2 at the beginning of this year, you were introduced some newer topics, and I do believe they are more difficult. Okay, so the first topic you are being introduced to is alkyl halides. Okay, so or what we call halogenal alkanes. So I will just put it as alkyl halides. Okay, so for alkyl halides, you learn about something unique. You learn about the fact that because one of the H in alkane is being replaced by a halogen, so there is a polarity difference, and then the carbon involved will take on a partial permanent positive charge, and because of that, it is susceptible to nucleophilic attack. That is when we introduce you to the reaction nucleophilic substitution. And in nucleophilic substitution in particular, you learn about two mechanism, SN1 and SN2. Okay, and to a very small extent, within the H2 curriculum, you also learn about elimination. Okay, so you learn about elimination over here. But those of you who are taking H3, you learn that elimination can also fall under two categories: first order elimination and second order elimination. And they follow the same rates determining step as SN1 and SN2 respectively. And then moving on to the next topic, you learn about hydroxy compounds. Okay, hydroxy. Okay, and then after that you learn about carbonyls. Okay, and finally before nitrogen compounds, you learn about carboxylic acids and derivatives. Okay, then for hydroxy compound, we did mention that there is no mechanism for you to work with, but truth to be told, if you look at the lecture notes, we do tell you that, for example, if you replace the OH with Cl via reaction with, say, thionyl chloride or PCl5, essentially that reaction is known as nucleophilic substitution. Okay, although you don't learn how to draw the mechanism, but the reagent will actually inflict nucleophilic substitution on the system. Yeah, so we do not require you to know how to draw, but you need to know how to name the types of reaction. Okay, for carbonyls, you learn the final mechanism known as nucleophilic addition. Okay, because the carbonyl carbon is electron deficient and therefore susceptible to nucleophilic attack by a nucleophile. And then for carboxylic acid and derivatives, you learn about a new reaction. Although you do not need to know how to draw the mechanism, but the type of reaction is known as nucleophilic acyl substitution, or in short we call it addition elimination. Okay, you do not need to learn how to draw the mechanism, so I'll just put in purple. So you either call it addition elimination, or you can call it condensation. Okay, or sometimes we can call it nucleophilic acyl substitution. Okay, it does take on different names, but by and large they mean the same thing. They are not synonymous 100%. Yeah, so I think as you go through your education in university, if you do take chemistry related courses, then I think you will have a better understanding. Okay, so right now we are at the final topic on nitrogen compounds. Okay, so I'll just bring you through. So basically there are four broad categories. Amines, I think you have learned about it. Okay, you have heard about amines from an earlier chapter, I think as early as alkyl halides. Yeah, if you recall, in alkyl halides, we mentioned that in order to produce amine, you need to subject the relevant halogenal alkanes with ammonia. Okay, or another way we can perform the synthesis if we want to do a step-up reaction, meaning to increase the carbon counts by 1, is to subject the halogenal alkane to ethanolic KCN. And then after that, we will perform a reduction in order to obtain the primary amine. Okay, so if you do recall, we did mention that in alkyl halide, so it's not new. Okay, what about phenylamine? Okay, so phenylamine will be a good contrast with phenol in hydroxy compounds. Okay, because phenol in hydroxy compounds is an acid. It's a very weak acid with pK about 10, and phenylamine, right, over here is a weak base. So it's actually a weaker base than amines because the lone pairs of electrons on the NH2 is partially delocalized into the phenyl ring. Yeah, so because of that, it is not as available to donate to a proton as compared to a normal amines. Yeah, so we will discuss that later on. Yeah, so if you take a look at the third bullet point, it mentioned about what are the effects of delocalization of lone pairs on nitrogen or phenylamine. Okay, then after that, the third category will be amides. You briefly learn about amides in carboxylic acid derivatives. Yeah, so and those of you who are doing biology, right, essentially amides is something which you are familiar with. Basically in biology, that particular functional group, because it's formed between amino acids, we call that a peptide linkage. Okay, so it's similar. Yeah, so amides in the laboratory, right, is formed between an amine and an acyl chloride. Yeah, so basically amides has this particular, it looks something like this. Okay, R and then maybe an R prime. Yeah, so this is what we call the amide linkage. Some people call it the amide bond, but strictly speaking, it is not a bond because it is a linkage between two groups. Okay, but I think in biology, the way it's being called tends to be a little bit loose. Yeah, so I think this is called the amide bond, but I think in chemistry we have to be a little bit more specific. And then very, very briefly, we'll be talking about amino acids, its properties and the type of reaction. Yeah, so just very briefly, okay? And then if you scroll down, you will be able to see some of the learning objectives which you are required to know, and I will not go through the list with you. Okay, you can look through on your own and then use it as a checklist for your revisions. Okay, so very quickly we will move to the introduction. Okay, so I think I will zoom out a little bit. Okay, so these are nitrogen compounds. Okay, so first of all, right, amines are being derived from ammonia. If you recall from halogenal alkanes, okay, in order for me to produce this particular primary amine, right, what do we do? Okay, so what we will do is we will react ammonia. So maybe I can just put out as a RCl. We'll react ammonia with RCl as a alkyl halide, or in this case chloroalkane. Okay, and in the process we will be able to generate the primary amine. Okay, then as all of you might have recalled, right, the primary amine itself is a stronger base as compared to ammonia because the R group is electron donating. So remember, yeah, in terms of electronic effect, alkyl groups is electron donating, so it will enhance the availability of the lone pairs of electrons, okay, over here. And because it enhances the availability of lone pairs of electrons, yeah, the primary amine is a stronger nucleophile as compared to ammonia, so it will continue to react with the RCl and in the process give us a secondary amines. Okay, and then this will continue, we'll end up with a tertiary amines. And then finally, because a tertiary amine also has a lone pairs of electrons on nitrogen, it will perform a final nucleophilic attack on RCl to give us a quaternary ammonium salt. Okay, so I think this name is quite interesting. You might just want to remember, it's called quaternary ammonium ions. It's an ion because the nitrogen takes on a permanent positive charge. Okay, as to why is it a positive charge, etc., you might want to review the videos which I've uploaded on former charges. I think that will maybe make life a little bit easier in understanding why the nitrogen will take on a permanent positive charge rather than one of the R groups. Okay, then another thing which I thought I want to highlight to you is that for the drawing of mechanism, right, let's say you would like to illustrate to, say, the examiner, you know, whatsoever, right, it is actually difficult for you to illustrate nucleophilic substitution like this. Okay, because it doesn't quite make sense, because you do not attack an RCl in this case. Yeah, so this is really not the most ideal way for you to illustrate the mechanism. Yeah, so sometimes for to make it more simply, I think it is easier if you can just write it as RCH and then Cl. Yeah, so that you can write out a permanent partial positive charge, and then your ammonia can then perform a nucleophilic attack. Take note that I'm not trying to attempt to draw the actual mechanism in its three-dimensional format. I'm just trying to show you how you have gotten a primary amine in this approach. Okay, so in the process, I will be able to get R, CH2 and H2 plus HCl. Yeah, so this is the primary amine, and then this will continue to react with another RCH2 Cl. Okay, and then I will then kick out the chlorine. Okay, and then this will continue to give us RCH2 and then CH2R, and then H, and then plus HCl. Okay, I think it is more accurate to represent the mechanism if you do want to draw it. But if that is not the case, then feel free to represent it the way your lecture notes represent. Yeah, because basically a primary amine has one R group attached to the nitrogen, secondary amine has 2, tertiary has 3, and the quaternary ammonium salt has 4. Okay, and then aliphatic. Okay, so example, ethylamine. I think the naming is given to you, ethylamine. Okay, so ethylamine has 1 alkyl group, so that is the ethyl group. And then for N-methyl ethylamine, it has an ethyl group and a methyl group as the 2R group. And then trimethylamine has 3 methyl group bonded to the nitrogen. And do take note that whatever we are talking about, right, the nitrogen has a lone pairs of electrons over here. Okay, for primary, secondary, and tertiary amines. Okay, but for the quaternary ammonium salt, it doesn't have a lone pairs of electrons anymore. Okay, so this is the quaternary ammonium salt with 4 methyl groups. So we will name it as tetramethyl ammonium ions. Right? And then for aromatic, we have phenylamine, N-methyl phenylamine, N-dimethyl phenylamine, and then N-trimethyl phenylammonium ions. And remember that for the quaternary ammonium salts, the nitrogen will take on a permanent positive charge. Remember that it is a permanent positive charge. It is not a partial positive charge. Yeah, please do remember that. Yeah, the only difference between the aromatic amines and the aliphatic one is that for the aromatic one, the lone pairs of electrons is residing largely at the p orbital, so it will partially delocalize into the phenyl ring. Yeah, so in terms of basicity, the aliphatic amines are more basic as compared to the aromatic amines. Okay, now, so remember that I think one of the misconceptions students might have is let's say I have something like this. Maybe I'll just illustrate it here. Okay, so if I have a phenyl ring, okay, if I have a phenyl ring, right, and then I have a CH2NH2, the students might misunderstand that this is an aromatic amine. It is not an aromatic amine. Okay, so let me emphasize, it is not an aromatic amine because the carbon directly bonded to the NH2, right, is sp3 hybridized. So this is considered an aliphatic amine. Okay, so for it to be an aromatic amine, right, the nitrogen in question has to be directly bonded to the phenyl ring. Okay, so remember that. And then for amides, they are derivatives of carboxylic acids. So we have primary amides, which looks like this. Okay, so basically primary amides is being derived from an acyl chloride. Okay, so in this case, my acyl chloride will be RCOCl and ammonia. Okay, so we will call this a primary amide. The rest are what we call substituted amides. Why is it called substituted amides? Essentially, you will notice that each of the hydrogen here is being substituted with R prime and then R double prime. Okay, then if you are asking me how can we get the substituted amides, oh, that's pretty straightforward. Okay, so remember that the primary amide is obtained from the relevant acyl chloride and ammonia. Then the substituted amide will be from the relevant acyl chloride and a primary amine. Okay, and then the other ones with the 2R groups will be obtained from a secondary amine. Yeah, do take note that you can't have 3R groups here for a very simple reason, because the final species is, if you ever draw it out, right, is actually a zwitterion, which you'll be introduced later on, and that particular species is not very stable for the case of a reaction between an acyl chloride and a tertiary amine. Okay, so just take note of that. So the most you can go up to is having 2 of the R group bonded to the N and not 3. Okay, and then amino acid where you have an alpha carbon. Okay, so again, those of you taking biology, you'll be more familiar. So you have an alpha carbon here, and this particular alpha carbon is bonded to both a carboxylic acid and an amine. Okay, and those of you who are sharp enough, you will notice that this particular species do not exist for long because a carboxylic acid has a protonic hydrogen and an amine has a lone pairs of electrons on the nitrogen. Yeah, so what exactly is happening here is that it will undergo internal acid-base neutralization reaction. Yeah, so the species which is likely to exist will be a zwitterion, which is the term I used just now. It will be a carboxylate here and then an ammonium salt over here. Okay, yeah, something like this. Okay, yeah, so with that, we'll move on to the nomenclature. I think we have sort of mentioned it just now. Okay, so simple amines name adding the suffix amines to the longest alkyl chain. So for 2 carbon will be ethane, right? So we just replace it with amine, so ethylamine. Yeah, so this is the alkyl groups. Remember, from alkane to alkyl, basically you remove one H and then you replace the ANE with YL. Yeah, so this is ethyl from ethane, so ethylamine. And then you have 2, you just name it as diethylamine. Okay, 3 will be triethylamine. Then after that, if I have a phenyl ring, it will be called phenylamine. Okay, and then I think the rest are details. So for example, this is not something which is unfamiliar. So we name it as the longest chain. Okay, so the longest chain is 5 carbon. Okay, so number is 1, 2, 3, 4, 5. So we have 5 carbon here. So first position is an amine, so we call it pentane 1 amine. But the third position is bonded to a methyl group, so we call it 3 methyl pentane 1 amine. Okay, then if I have secondary and tertiary amine, right, I will use the letter N to denote the position of the substituent on the nitrogen atom. Yeah, so for example, the parent of this, which is the longest chain, right? The parent is ethylamine. Okay, but because it's a secondary amine and the methyl group is bonded to the nitrogen in question, so we'll call it N-methyl ethylamine. Okay, and then the same case goes for this. Okay, so in this case, the parent is phenylamine, so it's phenylamine is the parent. Okay, and there are 2 methyl groups bonded to the nitrogen in question because it is a tertiary amine, so we'll call it N-dimethylphenylamine. Okay, yeah, so if there is a functional group of a higher priority, then NH2 will call it as an amino group. Again, let me emphasize that Cambridge rarely tests the students on nomenclature, so there isn't really a need to memorize all this lah. Yeah, but of course, once you have seen them long enough, then somehow they will get into your brain lah. Yeah, okay, so in this case, the longest chain is 3 carbon. Okay, so 3 carbon like this, so it's propanoic acid. Second position is NH2, so we'll call it 2 amino propanoic acid and not 2 amine propanoic acid, etc. Okay, so just make sure you name it correctly. And then for amides, similar to amines, whatever groups attached to the nitrogen, we will just call it, we will just name the group, name the position of the group with N. Okay, so okay, anyway, before that, we'll look at ethylamide here. Okay, so this is derived from ethanoic acid, so ethylamides, from benzoic acid, so benzolamides. Okay, so further substituent in this case, this is from propanoic acids. Okay, so we'll call it propanamides, but because it is not a primary amine, the nitrogen contains a methyl group, so we'll call it N-methyl propanamides. Okay, and then for our case here, this is from ethanoic acids, so we call it ethanamides, and the nitrogen is bonded to 2 methyl groups, so we call it dimethyl ethylamides. Okay, then same case goes for the amide derived from benzoic acid, so we call it benzalmides, and then the nitrogen is bonded to a methyl group, so we call it N-ethyl benzalmides. Right? Okay, so we'll have exercise 1.1 over here. So we need to name the following compounds and indicate whether it is a primary, secondary, or tertiary amine. Okay, so first of all, right, let us try to look at whether is it primary, secondary, or tertiary. What is the easiest way to look at it? Remember earlier on I mentioned that the easiest way is to look at the number of R groups bonded to the nitrogen. Okay, so in our case for 1, it has 1 R group, so it will be a primary amines. Okay, people do remember that we can represent primary as 1 degree, secondary as 2 degree, tertiary as 3 degree, but they should not be pronounced the way they are being written. So if you see this, it should be pronounced as primary amine and not 1 degree amine. Okay, yeah. In the case of this particular one, there's 2 R groups over here, so it's a secondary amines. Okay, yeah. The third one, it's of course an aromatic amine. Okay, so 1 R group, it is primary amine. Okay, and in our case here, 3 R groups, so it's a tertiary amines. Okay, yeah. I'm going to switch to red. Then how am I going to name it? Okay, so again, we will look at the parents. So this is likely to be the parents. So the parents will be cyclohexylamine. So cyclohexylamine. Okay, and then the second position has a chloro group, so it will be 2-chlorocyclohexylamine. Okay, then for the second one, again, the parents will be the one with the longest chain, so this is the parents. Okay, so it will be propylamines. Okay, so propylamines. Okay, and then the nitrogen is bonded to an ethyl group, so we'll call it N-ethyl propylamine. Okay, and then for the case of this, the parents is phenylamine, so it's phenylamines. Okay, and then in terms of substituent, second position substituted with a chlorine, fourth position with a bromine, but when we name the compound, it has to be in alphabetical order, so we'll call it 4-bromo, okay, and 2-chlorophenylamine. Okay, and then for tertiary amine, in our case here, the parent obviously in this case is phenylamines. Okay, so the parent is phenylamines. Okay, and then it has 2 substituent, a propyl group, okay, and a methyl groups. Okay, so remember that we need to indicate it with N, okay, to indicate that the substituent is bonded to the nitrogen. Okay, so in this case, going by alphabetical order, so we'll name it as N methyl, okay, and then N propyl phenylamine. Okay, the naming is a little bit systematic, can be boring, but it's not too difficult, and it's not something, it's not like a rocket science. Okay, Ken. So with that, we'll move on to the next segment on physical properties. One of the things which I often share with the students is that you will never want to smell amines above primary amine. Yeah, secondary and tertiary amines are really smelly. If you are thinking about what kind of smell you're expecting from amine, just go to the fish market, not supermarket, but the wet market, and then you just walk one round the stores selling fish, and then you will roughly have a sense of the kind of smell amines give. But those smells in the fish market is pale in comparison to those you use in your organic synthesis lab. Okay, yeah. So just try to imagine that amines will have that fishy smell times 10 or even greater. Yeah. So when I was doing my research as a JC student in the labs in NTU, we used a tertiary amine, and I can tell you that you never want to smell amines again. Okay. Anyway, back to the boiling point. You notice that what we have given you here is that when we increase the carbon chains from methylamine to ethylamine to propylamine, you notice that the boiling point increases from -6 to 17, and then from 17 to 50 degrees Celsius, I think you can attribute this to the increase in dispersion forces between the non-polar chain. Yep, so for propylamine, it has a greater non-polar chain as compared to ethylamine, and ethylamine a greater non-polar chain as compared to methylamine. Yeah, so in that case, the increase in boiling point is due to the increase in dispersion forces. Of course, the predominant intermolecular forces of attraction is still hydrogen bonding, as what we listed out here. Okay, then you will notice that for the straight chains, if you take a look at propylamines, if I branch it up, not exactly branch it up, but if I just split it up into two portions to give us a secondary amine, so we have a ethyl and a methyl, right? You notice that the boiling point actually decreases from 50 to 34. Yeah, so although the main intermolecular forces of attractions is hydrogen bonding, but you can attribute to the decrease in boiling point due to the fact that the whole molecule is more spherical in shape, okay, as compared to one which is more elongated. So in terms of the surface area for interaction via dispersion forces is being reduced, and that explains why there's a reduction in the amount of energy required to overcome the weaker dispersion forces between molecules of N-methyl ethylamine. Okay, Ken? Yeah, so and then moving on, when we branch it further, okay, so you have encountered this in chemical bonding as well. When we branch it further to give us a tertiary amine, you notice that the boiling point decreases drastically, okay, all the way from 34 to 3 degrees Celsius. And some of you might just explain it based on the fact that now the molecule is even more spherical, etc., etc. Yeah, but this is a misconception, because if you stare hard at the structure of diethylmethylamine, right, you notice that it doesn't contain a protonic hydrogen. Okay, it does not contain a protonic hydrogen. So that means that it is incapable of forming hydrogen bonding. Yeah, so therefore the main intermolecular forces of attractions we are looking at is largely permanent dipole interaction, as well as dispersion forces. Okay. Yeah, so dispersion forces is also known as instantaneous dipole-induced dipole interaction. Yeah, so that is something which we use synonymously between the two. Okay, I think the explanation I've given you here is listed out in the bullet points, so I think you can read them. Okay, then moving on, as a comparison between molecules with roughly the same number of electrons, we are looking at methylamine versus methane versus methanol, right? You notice that methanol has the highest boiling point amongst those with similar relative molecular mass, and then this is followed by methylamine, and this is followed by ethane. Yeah, so I think this will not come as a surprise, because the main intermolecular forces of attractions between ethane molecules is dispersion forces. So I think all of us agree that dispersion forces requires little energy to overcome, which explains why the boiling point is really low. How about hydrogen bonding? So the hydrogen bonding between methanol molecules, you would expect it to be significantly stronger than the hydrogen bonding between methylamine molecules. The reason is because nitrogen is less electronegative than oxygen, so the electronegativity difference between N and H is smaller than that between O and H. Yep, so the smaller electronegativity difference will thus create a smaller partial positive charge in the hydrogen in methylamine as compared to that in methanol. And because of that, the hydrogen bonding between methylamine molecules is weaker than that between methanol molecules. Yep, and because the hydrogen bonding between methylamine molecules is weaker than that between methanol molecules, I will need less energy to overcome them, and that leads to a lower boiling point. Okay, so if you are very familiar with concepts in chemical bonding, I don't think any of the stuff I've mentioned earlier on will be unfamiliar to you. Okay, so let's move on to the next portion. Okay, so amides, they tend to be white crystalline solids. Okay, yep, so in the solid state, it forms very well defined hydrogen bonding between the protonic hydrogens and the lone pairs of electrons on the carbonyl oxygen. And because they tend higher amides tend to have a very high relative molecular mass, so they tend to be solids. Yeah, so for the smallest one, which is methylamide, it is a liquid. Okay, so they are able to form extensive intermolecular hydrogen bonding. So that explains why amides other than methylamides tends to be crystalline solids. Okay, yeah. In terms of solubility in water, it works the same way as hydroxy compounds. Okay, so those with low relative molecular mass tends to be very soluble in water because of the hydrogen bonding it can form with water molecules. Okay, other than that, if the carbon chains become longer and longer, then they are virtually insoluble because the hydrogen bonds formed between the protonic hydrogens of the amines with the water molecules is probably insufficient to overcome the very strong dispersion forces between the phenylamine and the amines with large R groups. Okay, so because of that, then I would expect the solubility to be very poor. Yeah, and amines tends to be very soluble in non-polar solvent. Yeah, because the non-polar groups can form strong dispersion forces with the non-polar groups of the non-polar solvents. So usually we are looking at, say, benzene or hexane. Okay, yep. So with that, I'm going to move on. Amides follow the same idea, tends to form extensive hydrogen bonds. So the simple amides are very soluble as well, but those with a huge R group tends to be insoluble. I think it works the same way. Okay, so with that, we'll move on to exercise 2.1. 2.1a, propylamine is highly soluble in water, and draw a diagram to illustrate how a molecule. So let's take note of the article. A molecule of propylamine, how does it interact with a molecule of water? Okay, so we'll try to do that. So we'll draw the propylamine, so 3 carbon chains. So propylamine will look like this, 3 carbon chain, and then with a nitrogen and H and H. Remember, from chemical bonding, when you are showing hydrogen bonding, make sure you show the dipoles. Okay, delta minus, delta plus. Okay, and then I'm going to show water molecules. So I will form my hydrogen bonding with the protonic hydrogen of the amino group, and then the lone pairs of electrons. Remember to draw it out. Okay, and then oxygen and H and H. Oops. Okay, H. Okay, so delta minus, delta plus. Remember to label your hydrogen bonding. Okay, most of the time in assessment, you lose marks because you guys forget to label the hydrogen bonding. Okay, so this is hydrogen bonding. So I'm going to label it hydrogen bonding. Okay, yep. So I think that should be fine. And then for part B, explain why this particular compound, 1,2-diaminoethane, okay, has a boiling point of 116 degrees Celsius, okay, whereas propylamine has a boiling point of just 50 degrees Celsius. So they have quite similar relative molecular mass. Okay, so for 1,1-diethylamine, let me just try to draw it out. Okay, it looks like this, NH2, and then NH2. Okay, you notice that 1,2-diamino ethane, right? It has more protonic hydrogen as compared to propylamine. So if I'm going to just highlight the protonic hydrogen, so there's one here, and then in this case there are 4. Yeah. So because of that, I expect 1,2-diamino ethylamine to be able to form more extensive hydrogen bonding between molecules as compared to that between propylamine molecules. Yeah, so because of that, I will require more energy to overcome the more extensive hydrogen bonding between 1,2-diamino ethane molecules as compared to that between propylamine molecules. Okay, so because I need more energy to overcome, I would expect a higher boiling point. Alright, so with that, we'll move on to section 3 on the basicity of nitrogen compounds. Similar to acidity, for basicity, we need to look at an easy model for us to determine whether an amine is a strong or weak base. Yeah, so if you recall from acidity, to determine whether an acid is a stronger acid than the other, right, we need to look at the stability of the conjugate base relative to other acids which you are comparing with. Yeah, so when you're looking at the stability of the conjugate base, we largely focus on whether the negative charge can be delocalized into any possible groups, or whether the electron density at the group with the negative charge can be inductively withdrawn. Yeah, so for basicity, we look at the availability of the lone pairs of electrons to coordinate to a proton. Okay, so I guess it's listed out over here, lone pairs of electrons, nitrogen, yeah, so to coordinate with a protons. Yeah, so the more available the lone pairs of electrons is, then the stronger is the base. Okay, if you need to review on reaction and stoichiometry for the theories of acids and bases, please feel free to click on the relevant link to the videos which I have done up for the topic 4 on reactions and stoichiometry. Okay, so we'll move on to the next portion on the basicity of amines in the gaseous phase. Okay, so I think there is a need for you to understand this term gaseous phase. It's not in the solution phase, so there is a slight difference. Okay, so as what you have recalled from us, our discussion earlier on, right? We understand that LQ groups are electron donating. Yeah, so the more LQ groups the nitrogen is sigma bonded to, you would expect the electron donating effect to be more prominent. Yeah, so that will increase the availability of the lone pairs of electrons to coordinate to a protons. Yeah, so from this particular diagram, I think we can expect that a tertiary amine is a stronger base as compared to a secondary amine, and then secondary amine is a stronger base as compared to a primary amine, and then primary amine stronger base as compared to ammonia. Yeah, but this argument is only true for the gaseous phase, because for the gaseous phase we ignore one important reason, that is the steric factor which is imposed by the R group. Okay, so in the next section we are looking at the basicity of amines in the aqueous medium. So in our case here, we need to recall what we learned in acid-base equilibrium. Yeah, so in acid-base equilibrium, we know that a weak base will partially ionize in water to give the relevant conjugate acids, okay, and then OH minus. So we are able to write Kb and then of course define pKb. Yeah, so the larger the Kb value is, the greater the basicity, the smaller the pKb, the stronger the base. Okay, so with this idea, we will need to look at phenylamines. Okay, so for phenylamine, right, they are considerably less basic than ammonia. I think we sort of mentioned it earlier on. So if you look at the baseline ammonia, the pKb is 4.74. Okay, whereas for a primary amine, it's about 3.35. You can understand that because the electron donating group increased the electron density of the lone pairs of electrons on the nitrogen, and thereby increases its availability to donate to a protons. But for phenylamine, the pKb is 9.40, so it is close to 100 times weaker than ammonia. Why is that the case? Okay, so it has been explained using the orbital diagram here, because the lone pairs of electrons partially delocalize into the phenyl ring, and this reduces its availability to coordinate to a protons. Okay, this is the resonance structures which it's not a requirement for H2 curriculum. So you notice that how we draw the resonance structures to showcase the delocalization is, first we push the lone pairs of electrons to form the pi bond between N and H over here, and then after that one of the pi electron club will break towards the carbon, and then in this case the carbon will bear the negative charge. Okay, yeah. Some of you might be, especially those of you who did not do H3, you might be confused by the drawing of resonance structures. So like, you might be asking, so what is the point in drawing all these resonance structures? So, yeah. So basically, right, what I often share with students is that all these drawing of resonance structures to showcase how the lone pairs of electrons can be pushed into the phenyl ring, it simply represent what we show you over here in the orbital diagram, except that we are using a slightly more sophisticated model in terms of drawing of resonance structures to explain this orbital overlap. Yeah, but in reality, right, the most prominent resonance structures for phenylamine is indeed simply just the neutral version, which is this. Yeah, so do not expect that the electron density just move around the ring, and then it's like it go in for a ride and then out, and then go in for a ride again and then out. No, it doesn't happen that way. Okay, so what you are expecting is always a model that is in between all of these. Yeah, so if you just try to imagine that the real structure of phenylamine is somewhere in between all of this, but closest to the neutral version. Okay, as I explained to you the reason already, because the lone pairs of electrons on nitrogen will partially delocalize into the phenyl ring, and nitrogen is more electronegative as compared to carbon, so there is no reason for the carbon to bear the negative charge. I mean, bear the lone pairs of electrons, like in this case, because it gets delocalized in the resonance structures, it will bear the negative charge. Yeah, so between carbon and nitrogen, nitrogen prefers to take on the lone pairs of electrons because nitrogen is more electronegative than carbon. Yeah, so if you are able to view chemistry or structures in this manner, then you will be able to quickly recognize which is the more likely resonance hybrid or resonance form of phenylamine. Okay, yeah. Then for substituted phenylamine, I think this needs no introduction because we have earlier on highlighted examples using phenol. Yeah, so it's a similar story. So if I have electron donating groups, the electron donating group will increase the electron density of the benzene ring. Okay, and because it increases the electron density of the benzene ring, right, the result is that the lone pairs of electrons will delocalize to a smaller extent into the phenyl ring. Yeah, so in that case, electron density at the nitrogen will be more available to coordinate to a H+. Yeah, so in a similar story, right, electron withdrawing group will withdraw electron density away from the phenyl ring. And when the electron densities is being withdrawn away from the phenyl ring, this results in the lone pairs of electrons on nitrogen to delocalize to a greater extent into the phenyl ring, thus making it less available to coordinate to an acid. Okay, so when we say acid here, we are really talking about either a Lewis acid or a proton. Yeah, so in that case, we expect having an electron withdrawing group to make the substituted phenylamine to be a weaker base. Okay, and donating group will make it a stronger base. Right? Okay, so I think we have the necessary data over here. So the donating group, you can see that the pKb drops from 9.4 to 8.92, and then the withdrawing group increases the pKb from 9.4 to 13.0. Okay, yeah. And then for amides, amides is neutral. Okay, largely we will consider amides to be neutral. Why is that the case? Because between oxygen and nitrogen, oxygen is more electronegative than nitrogen. So you would expect the lone pairs of electrons, okay, on the nitrogen to delocalize to a very large extent over to the oxygen. Yeah, so in fact, the oxygens will take on quite a permanent partial negative charge, and the nitrogen quite a permanent partial positive charge. Yeah, but in our case here, because we are drawn this resonance structure, right? So the extreme end of the resonance structures, you will see that the oxygen takes on a permanent -1, and then the nitrogen takes on a permanent +1. But the real structure is in between the two, something like this, and that's why earlier on I said that it takes on a permanent negative charge for the oxygen and permanent positive charge for the nitrogen. Okay, yeah. So largely we will think of an amide as a neutral species rather than a base. And because of this huge extent of delocalization, you expect the CN bond to have a very prominent partial double bond character. Yeah, so that makes bond rotation difficult. Yeah, so for those of you taking bio, you might have heard of something called the Ramachandran angle between the amino acid residue, between two planes of the amino acids. Yeah, so if you have not heard of it, then I think it's fine. If not, you can go and Google it, and then maybe you can read more about it. Okay, so the relative basicity of ammonia, ethylamine, phenylamine, amide is as follows. So you notice that for amide, it is even a weaker base than water, if you just compare it that way. Then phenylamine, of course, lone pairs of electrons, partially delocalized into the phenyl ring, and then makes the lone pairs of electrons less available. And then ammonia is the benchmark. And then of course ethylamine, you have a ethyl group donating electron densities towards the nitrogen, so enhancing the electron densities of the lone pairs of electrons, making a stronger base as compared to ammonia. Okay, so we have an exercise 3.1. So you are asked to arrange the following compounds in order of increasing basicity. Okay, so in the simplest fashion, let us try to identify whether there's an amide. So we can see that there's an amide here. So obviously, if there's an amide here, then I would expect amide to be the weakest base. So I will write it on the extreme left. Okay, and then you'll notice that we have two phenylamine. Okay, then one is a chloral group which is inductively withdrawing, and then we have a methyl group which is electron donating via the hyperconjugation effect. Yeah, so because of that, I would expect the lone pairs of electrons on A, right, to delocalize to a smaller extent due to the fact that the electron donating methyl group increases the electron density of the phenyl ring. So I will put A on the extreme right. And then, of course, in the middle, I expect B to be having a basicity lower than that of A, because the inductive withdrawing Cl group will withdraw electron density away from the phenyl ring, and in that case, it allows the lone pairs of electrons on the NH2 to delocalize to a slightly greater extent as compared to that of A. Okay, so with that, then this will be the order, and I've explained to you in my narration. Okay, next we'll move on to the basicity of amines in the aqueous phase. I think this is in contrast with what I mentioned to you earlier on over here. Okay, so over here, right, if we simply look at availability of lone pairs of electrons of amines in the gaseous phase, I think we all agree that tertiary amine will be the strongest base. Will be a stronger base as compared to secondary, and then secondary will be a stronger base as compared to primary. Yeah, but remember earlier on I mentioned about the steric factor. So if you incorporate steric factor in, then maybe we are expecting something different. Okay, so with this, you notice that for ammonia, the baseline is 4.74. Okay, then you notice that the primary amine, right, with a R group, in this case is a methyl group, right, the basicity dropped from 4.74 all the way to 3.35. Okay, and then with an extra methyl group, it drops relatively little. Okay, so that's just a very small drop. Yeah, so you can argue that maybe it's due to the steric demand imposed by the methyl group. Yeah, and then what is very and please take note of it, this is talking about in the aqueous phase. Okay, we're not talking about gaseous phase. Okay, and then an extra methyl group, right, will result in the pKb shooting up to 4.21. So therefore, from here you can see that the tertiary amine in the aqueous phase is actually a weaker base as compared to a secondary and primary amine. Okay, yeah, so if I ask you to predict it at the gaseous level, right, you expect the tertiary amine to be the strongest base. Yeah, however, in the aqueous phase, we have a slightly different story to tell. Yeah, in addition, of course, to the steric demand we introduced to you earlier on. Okay, so remember that we are looking at the availability of lone pairs of electrons to coordinate to H+. So if we have more R group, then we are expecting the lone pairs of electrons to be harder, okay, to be interacting with the H+. Okay, and of course, from another angle, when we are looking at the, I think if you read the paragraphs over here, it reads that in the aqueous medium, tertiary amines are less basic. The resulting conjugate acids are not as effectively solvated through hydrogen bonding. Okay, so what do we actually mean from here? Okay, so for example, right, this is another reasoning we can look at. So if we have this tertiary amine, right, the protonated form will look something like this: CH3, 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 and then H, and then plus. Yeah, because this structure is relatively bulky. Why is it bulky? It's bulky due to the methyl group. Then it makes it more difficult to be solvated by water molecules. So the water molecules will have a a more difficult time forming ion dipole interaction with it. And because of that, right, it is less stable, okay, as compared to the conjugate acid of a primary and a secondary amine. Okay, yeah, so with that reasoning coming in, I hope you can understand what this paragraph really means. Okay, so with that, we'll move on to section 4 on the preparation of amines and amides. As mentioned earlier on, right, amines can be prepared from the nucleophilic substitution of halogenoalkanes as well as the reduction of nitriles. If you need review, please click on the link below to topic 15 on halogen derivatives. We can also obtain amine from the reduction of amides, which we will cover later in this particular topic. And then specifically for phenylamine, we can get it from the reduction of nitrobenzene. Okay, so this is a very specific condition which I think you need to be aware of for your H2 curriculum. The reagents needed is tin in excess concentrated hydrochloric acids, okay, and then you need to heat it. Yep. And when you are performing this particular reaction, because the system is acidic, okay, you will first obtain the conjugate acid of phenylamine. Yeah, so that is why you need a step 2 where sodium hydroxide is being added dropwise to regenerate phenylamine, and it's usually regenerated as a white PPT. Yep, and some of you might be wondering, why is there a need for corn hydrochloric acid? Okay, so the reason for the corn hydrochloric acid is to convert tin into tin 2 plus, and tin 2 plus it will act as part of the reducing agent where it will coordinate to the nitrogen group. Okay, yeah, so we won't go specifically into the mechanism. If you are interested, you can review more about it in more advanced textbooks. Yeah, do take note that lithium aluminum hydride and sodium boron hydride are not to be used in the above reaction. The reason being they do not reduce the nitro group directly into amino groups. Okay, especially the case for sodium boron hydride. Okay, for lithium aluminum hydride, it will be reduced to an azo compound where you can still see the structure of the N double bond N, and this will bind or link up the two phenyl ring. Yeah, so if you accidentally write in lithium aluminum hydride in dry ether, then you'll be marked wrong because the final product will not be phenylamine. Yep. Okay, amides can be obtained from the condensation from acyl chloride, which in the earlier topic on carboxylic acid and derivatives, we have covered that, so I don't think we'll go into details here. If you need the details, please refer to topic 18. Yep, and do remember from topic 18 that carboxylic acid being acidic and amines being based, you cannot react them directly because they will rather undergo acid-base neutralization reaction like this. Okay, so in order for you to prepare amides, you must use a more reactive version of carboxylic acid, in this case acyl chlorides. Okay, yeah, so with that we can work on exercise 4.1. Okay, so for 4.1a, you are required to give the reagents and conditions that you would use in the following conversion. Okay, yeah, so do remember that from benzene all the way to phenylamine, you cannot introduce a NH2 electrophile. Yeah, so we all discussed earlier on that it is not possible. So for us to get phenylamine, you know that we require the reduction of nitrobenzene. Okay, so we need reduction of nitrobenzene, and the condition you can just copy what you have earlier on. So that will be tin excess corn HCl. Okay, corn HCl, and then I need to heat it. So this is condition number 1, heat. Okay, and then after that, this is followed by adding sodium hydroxide aqueous to generate phenylamine. Okay, and I don't think it will be difficult for you to predict how to get nitrobenzene. So in order to get nitrobenzene, I can simply perform electrophilic substitution, where I will be using corn sulfuric acids, okay, and corn nitric acid. And remember that this is a very specific condition for benzene to nitrobenzene. So you need to state the exact condition. So that is maintaining at 55 degrees Celsius. Okay, so maintains at 55 degrees Celsius. Okay, yep. So next we'll look at part B. From methylbenzene to this particular amides. Okay, shouldn't be surprising as well. Okay, so you should be able to predict how to get the amides, because the precursor is likely to be an acyl chloride. Why is it an acyl chloride but not carboxylic acid? I think we have answered this question earlier on. Because acyl chloride is the more reactive version of carboxylic acid. Okay, so that's one reason, so that the condition can be kept mild. And another reason, obviously, is because carboxylic acid, and in this case, we are going to introduce ammonia here, will prefer to undergo acid-base neutralization reaction. Yeah, so there is a real need for us to convert the carboxylic acid to the acyl chloride before subjecting the acyl chloride to excess ammonia. Okay, then before we get the acyl chloride, obviously we will need the carboxylic acid. So we will subject the carboxylic acid, in this case benzoic acid, to PCl5, okay, so that we can get the acyl chloride, right? And how are we going to get the benzoic acid from methylbenzene? If you recall from the chapter on benzene or arenes, you know that you can simply subject methylbenzene to KMNO4. So okay, so maybe I should just write it here so that it's not so confusing for you guys. Okay, so it's like this. Okay, so I can just subject it to KMNO4, H2SO4, and I will hit under reflux. Okay, and then that should be a sufficient condition for me to convert methylbenzene to benzoic acid. Okay, then the next portion is I'm going to get propylamine from ethene. So you notice that there is an additional carbon, so that will represent a step-up reaction. So I'm going to highlight the additional carbon. Yeah, so I hope this will look familiar, because we have done something similar in our examples on halogen derivatives. Yeah, so we can simply perform a reduction on a cyano group, so which will need lithium aluminium hydrides, okay, in dry ether. Okay, so in this case, we will get the cyano group as the precursor. Okay, so this is CN. And how do we get the cyanide in? Okay, so I'm sure you should be able to predict that before we get the cyanide in, we need to perform nucleophilic substitution on CH3, CH2Br, that will be bromoethane. Okay, so the reagents and conditions we need will be ethanolic KCN, heat. Okay, so this is simply an SN2 to give us the cyano compound. Okay, and how do we get bromoethane from ethene? I think we can easily just subject ethene to HBr gas. Okay, so this step will be electrophilic addition. Okay, so I hope you'll find the topics on nitrogen compounds quite straightforward, because quite a lot of things you have already learned them in the earlier topics. Yeah, so I think nitrogen compounds is basically just to sum all the topics up together and for you to see the link between the various parts of the topics. So the real need for you to revise on nitrogen compounds is just maybe half the curriculum requirement, because the other half you have already learned them in the earlier topics, especially halogen derivatives and carboxylic acids and its derivatives. Okay, so we'll move on to the next portion on the reactions of amines and amides. Again, you will be familiar with most of what I'm going to go through, so I'm going to not spend too much time on this particular section. Okay, so what we mentioned earlier on still remains. Chemistry of amines dominated by the presence of the lone pairs of electrons on nitrogen. So in that case, they can behave as a base to abstract H+. Okay, it can be both a Bronsted base or a Lewis base, because amines can also coordinate to an electron deficient site, such as aluminium in AlCl3. Okay, or they can act as good nucleophiles. Okay, so nucleophilic substitution, I think is not something you're not familiar with, and they can behave as excellent ligand for transition metal chemistry. Okay, so that will be topic 22. So please remember to look out for the relevant section on topic 22. Okay, then in the next segment, we're talking about reactions with acids. This is simply acid-base neutralization condition. So you don't really need reagents and conditions because it can be performed at room temperature. Okay, so either we use mineral acid or carboxylic acids. Okay, then after the acid-base reaction, the corresponding conjugate acid is highly soluble in aqueous solution. The reason being they can form favorable ion-dipole interaction with the water molecules. Yeah, so if you remove all the water, then the final compound can be obtained as an ionic salt. Okay, yep. I think over here there is a little point here. So amines with bulky R groups are insoluble in water. Okay, why is that the case? Again, I think we mentioned under the section on solubility. Yep, the reason being because the hydrogen bonds formed between the nitrogen and water molecules, right, is probably insufficient to overcome the dispersion forces between the huge R group. Okay, or you can say that the steric demand imposed by the R group, right, will prevent hydrogen bonds formation. Yeah, so there are several ways you can go about explaining for its insolubility. Okay, so one way for us to so-called force the amines to dissolve, right, is to convert it into a soluble ionic salt via acid-base neutralization reaction. Okay, like the above. Okay, so I'm going to explain it using the diagrams below. Okay, so this particular diagram, right, I have a mixture of phenylamine and cyclohexane. Yeah, so they are miscible. So I need to think of a way to separate them because I cannot simply just add water to them, because if I just add water to them, right, they will just float on top of water. Okay, so what I need to do here is I need to introduce a mineral acid that's 10% HCl. And then, of course, before I introduce the acid, I need to make sure that cyclohexylamine and cyclohexane, right, are dissolved in the relevant organic solvents. Yeah, so after I introduce the mineral acid, right, you notice that the cyclohexylamine will undergo acid-base neutralization. So in the process, it will form this ammonium salt. And the ammonium salt prefer to dissolve in the aqueous medium. So what's going to happen is that you are going to get the bulk of the cyclohexylam ammonium salt in this particular portion, okay, which is in the aqueous layer. The reason why the aqueous layer floats on top of the organic layer is because dichloromethane is denser than water. Okay, so there's no mistake here, not to worry. Yeah, and then you are going to expect the cyclohexane to be found largely in the organic solvents. Okay, so what we need to do is we are just going to separate out the bottom layer from the top layer. So the bottom layer will be the organic layer, and then I just need to evaporate dichloromethane off for me to get cyclohexane. Yep, and then for the aqueous layer, what I have here is the ammonium salts. Okay, so or the conjugate acids. So in order for me to get cyclohexylamine, what I need to do is simply just to add sodium hydroxide dropwise in order to generate cyclohexylamine as the white PBT. Okay, yeah, so that's what can be done. I think I don't need to go through with you the paragraphs here. You can read on your own, and then you'll roughly understand what I have just explained to you in this particular diagram. Okay, yeah, so next I'm going to move on to nucleophilic substitution, which again I do not need to talk too much about it because we have gone on great length to discuss about that in the topic on halogen derivatives. Okay, for a condensation reaction to get the relevant amides, it has been covered under carboxylic acids and derivatives, and they only react with acyl chloride. Okay, so I don't think we need to discuss. Electrophilic substitution of phenylamine will behave in a similar fashion as phenol. The reason being the lone pairs of electrons on the NH2, right, will partially delocalize into the phenyl ring, and in this way, right, it will enhance the electron density of the phenyl ring. And the enhancement of electron density at the phenyl ring, right, will thus require no Lewis acid for me to generate the electrophile. Yeah, so the phenyl ring itself can generate its own electrophile from bromine. In this case, bromine, when it's dissolved in the aqueous medium, right, the water will polarize the Br electron cloud. Yeah, so this will help in accelerating the rates of electrophilic substitution further. Yeah, so in our case here, because it is highly susceptible to electrophilic substitution, similar to phenol, we are going to get the 2,4,6 tri-bromo products, okay, at the end of the day. So your observations will be the yellow-orange solution decolorized, the white PPT will be this particular white PPT, and similar to phenol, if it is a substituted phenylamine, we might not get a white PPT because it might appear just as, as an oil. So it's difficult. So the white PPT is not the best observation. The best observation will be the yellow-orange solution decolorized. Okay, and because we are using aqueous solution, right, most of the time we might not be able to observe the white films of HBr unless our aqueous medium contains very little water. Yeah. Okay, so I think there's a comment here saying that the NH2 is 2,4 directing. I do not need Lewis acids. Okay, I've explained to you earlier on. And then, yep, I think I've covered all this, so I think I can just skip this portion. I will just jump straight into amides. Okay, so we talk about it as well. The lone pairs of electrons delocalize to a large extent to the carbonyl oxygen. So the electron density is greatly reduced, so it's not able to act as a nucleophile. Yeah, so largely amides are neutral. Yeah, but for amides, they undergo a special kind of reaction known as hydrolysis, but we'll talk about that later on. Before that, we are going to talk about the reduction. Okay, the mechanism of the reduction, it's not in your curriculum, so you do not need to discuss it. Yeah, but what exactly is happening here is that when you are reducing amides, essentially it can be viewed as just simply removing the C double bond O and replacing it with the two H's over here. Okay, if you are interested in the mechanism, you might just refer to more advanced texts. Okay, but basically the mechanism is similar to carbonyl chemistry. So it involves nucleophilic addition of the activated hydride in aluminum hydrides. Okay, yeah. There might be a portion which I thought I just want to tell you. I mean, not really a portion, but just for compare and contrast purposes. The reduction of amides is in your syllabus. Okay, so there's no doubt about it. Yeah, so this is in the syllabus. Okay. And when you reduce a primary amide, you get a primary amine. Okay, so if you are going to reduce a substituted amide, for example, something like this, okay, same case, I'm going to perform reduction. I will end up with, in our case here, the secondary amine. Okay, so I think this is in the syllabus, so you need to be aware of it. Some students might ask, oh, my friends in other colleges, or I read about it, that lithium aluminum hydride can also reduce ester. Okay, so maybe let us compare and contrast the reduction of ester as opposed to amides. Okay, so for example, for ester, right, let's say it's R1 and R2. If I'm going to perform the reduction using the same condition, lithium aluminum hydride in dry ether, right, I do not get the same kind of product as what I'm expecting from amides. Okay, rather I'm going to get 2 alcohol from here. So R1, and then I'm going to get CH2OH plus R2OH. Yeah, so this is a little bit different from the reduction of amide. I know a lot of you will be thinking, why is that the case? Okay, so again, I'll leave you to go and explore it in more advanced texts. Even introductory organic chemistry texts, sometimes they will explain to you. Yeah, but what I've written in blue is not in the syllabus. So you're not required to know the reduction of ester, but you are required to know the reduction of amides, which comes across to me as a little bit strange. But anyway, that's how the curriculum is being written. So I guess you just have to come to terms with it. Okay, the next segment on the hydrolysis of amides is simply the reverse of the condensation reaction. So when I hydrolyze amides, basically I'm breaking this activated CN bond, and in the process I'm going to produce the carboxylic acid and the ammonium. Okay, yeah, so if it's a substituted amide, then I will get the corresponding primary or secondary amine. Yeah, there are two ways you can go about performing this reaction. As per all hydrolysis, you can either do acidic hydrolysis, or you can try to perform basic hydrolysis. Yeah, but do remember that when you are performing basic hydrolysis, you are going to obtain the carboxylate salts, and you're not going to get ammonium. You're going to get ammonia, which can be driven off by heat. Yeah, so do remember, or do be a little bit careful what you want to discuss, or what you want to obtain at the end of the day. Yeah, and do remember that if you are reducing a primary amide, you're going to get ammonium, or if you are doing it in basic medium, you're going to get ammonia. Yeah, so that could be a good test for primary amide. Yeah, so after reduction, you can simply heat it to generate the ammonia, and you test it with moist red litmus, and then it should turn moist red litmus blue. Yeah, so that is one test you can do. Okay, and this is often something which the students cannot remember, because they might not know how to distinguish between amide and something else. Yeah, because if you recall, right, amongst all your distinguishing tests, you do not really learn this distinguishing test for carboxylic acid derivatives. Maybe except for acyl chloride, when you add water and then it will generate HCl, then you can observe the white fumes. But other carboxylic acid derivatives, you do not really have any distinguishing tests. Unlike aldehydes and ketones, where for aldehydes, it will give you a positive silver mirror with Tollens reagent, or for non-aromatic aldehydes, brick red precipitate with Fehling's reagent. Yeah. For carboxylic acid derivative, you do not learn anything except in maybe acyl chloride. And in our case here, this might be a case worth remembering for amides. Okay, simply perform an alkaline hydrolysis, heat it, and then you should get an alkaline gas which will turn moist red litmus blue. Okay, yep. I think it's written here that it can be used as a distinguishing test. Yep. You might be asking, what about amines? Can amines be distinguished the same way? Well, I mean, I have to say that for amines, they might not be as volatile as ammonia, but sometimes if you really run out of choices on what to do, then maybe you can also use moist red litmus to distinguish the substituted amide. But usually, amines have relatively high boiling points. Okay, so just something which you might want to remember. Okay, so I'm going to do exercise 5.1, predict the products of the following reactions. So N,N-dimethylamine, okay, and ethanoic acid. Obviously, this is ethanoic acid, so I'm just going to expect acid-base neutralization reaction. Okay, so I'm just going to draw the product, so like that. Oh, sorry, shouldn't be drawing a carbon, should be drawing a nitrogen. Okay, H plus. Okay, that's ammonium salts and ethanoates. Okay, so this will be my answer to 5.1a. Okay, for 5.1b, because I have two activating amino group on the phenyl ring, so I'm going to expect the products to be a multiple substituted benzene ring. So I'm going to have Br all over the place. Okay. Yeah, but sometimes for steric consideration, you might not get Br all over the place. But for simplicity, I think in our case here, we can safely say that it's going to be a multiple substituted product. Okay, and what about this? This is something interesting because it's not something which you have learned above. It's a special functional group. Okay, similar to an acid anhydride, but it's not called an acid anhydride. Yeah, yeah. But what you can predict here is that it is amide-like. Okay, so amide-like. So I'm going to just highlight the amide-like structure here. Okay, so the activated CN bond will be over here and over here and here. So I'm going to expect the hydrolysis reaction to break this bond and this bond. Okay, yeah. So in the course of the reaction, because they did not add acid at the end of the day, I'm going to end up with the carboxylate anion. Okay, O minus. Okay, and then O minus plus and H3. Okay, so if I'm going to ask you to predict how I can obtain this particular cyclic product, I think you should be able to tell me that, yeah, I'm going to use ammonia and the acyl chloride version of this. Okay, so what is the acyl chloride version of this? That will be something like this. Okay, Cl and Cl. Okay, so this ammonia and this diacyl chloride will be able to give me this particular cyclic 5-membered ring. Okay, sometimes you'll be asked to make relatively interesting compounds. Okay, and not to forget, because the question asks the products, so remember the products. Okay, I cannot give a carboxylate salts as the product, or rather I cannot give the carboxylates as the product. So I must be able to write out the salts. So I must be able to remember to introduce the counter cation here. Okay, so remember this. When they wanted products, make sure you give the products, the ionic products. You shouldn't be simply giving the species, which is the dicarboxylates. Okay, so you need to read the questions carefully when you are running through your exam scripts or even tutorials to begin with. Okay, at the beginning when you're learning it, you need to go through the tutorials, right? So you have to be a bit careful what is being asked of you. Okay, next I'm going to move on to the section on amino acids. Okay, I don't want to pretend to be a biology major because truth to be told, I have not taken any biology courses, but I do take certain courses on biochemistry when I was a student in the past. Yeah, so the kind of amino acids which you need to be aware of for H2 curriculum is just very, very minor. Basically, you are just introduced to alpha amino acids, okay, and it has certain structural features which you need to be aware of. They have a special name. They call it alpha amino acids because the amino group and the carboxylic acid group, right, they are bonded to the same carbon, which is what we call the alpha carbon. Yeah, remember that the carbon next to a functional group, we always designate it as alpha. Yeah, and amino acid has a special kind of structure in a sense that for alpha amino acids, not only is the alpha carbon being bonded to a carboxylic acid group and an amino group, but it is also bonded to a H, okay, and then the other end is bonded to an R group. The R group can take on different forms. So I think there are about 20 kind of different R groups for naturally occurring amino acids, which we are going to show you in the next 2 pages. Okay, yeah. In case you are wondering, right, are there non-alpha amino acids? So yes, there are. Like for example, this particular amino acid known as GABA or gamma aminobutanoic acid. You notice that the carboxylic acid group is bonded directly to this alpha carbon, but this alpha carbon is not bonded to the amino group. Yeah, so instead the amino group is bonded to the beta carbon. Sorry, the gamma carbon. So alpha, beta, gamma. Yeah, so it is like 3 positions away. Yeah, okay. Formation of zwitterions, I think I mentioned that earlier on, because the amino acid contains both an acidic group and a basic group, right? So they will undergo intramolecular acid-base reaction. What you're going to end up with is a carboxylate salts on one end, or carboxylate anion on one end, and then the ammonium cation on the other end. So this is known as dipolar ions, no overall electrical charge. We call this a zwitterion. Yeah. So the knowledge of zwitterion is required in your syllabus, which is being highlighted by learning objective 19. Okay, but you do not need to know isoelectric point. Isoelectric point used to be in the H2 syllabus, in the old syllabus, but it's not a requirement for the new curriculum. Yeah, so if you are interested, you can ask your bio friends on it, or you can just read up about it. Okay, yeah. So in the aqueous solution, amino acids exist as zwitterions because it is highly soluble. I mean, it can be highly soluble in water because both ends can form favorable ion-dipole interaction with the water molecules. And in the solid states, it exists as a zwitterion as well because it's able to form strong ionic bonding between the zwitterionic species. Okay, so many of the physical properties of amino acid will resemble that of ionic compound, except that their melting point tends to be much lower because of the larger molecular size. Okay, yeah. So physical properties of amino acids. So solid state wise, high melting point. For example, glycine. Glycine is where R is equal to H. It has a high melting point of 262 degrees Celsius. So it's due to strong ionic bonding or ionic interaction between oppositely charged ends of the molecules. Yeah, okay. And sorry, not molecules, of the zwitterionic species. I think you have to be a little bit exact in the way you express yourself, even verbally or even in words in exams. Yeah. You will also notice that, I think I mentioned earlier, highly soluble in water. Because of the strong ion-dipole interaction it can form between the zwitterions and water molecules, and because depending on the nature of the R group, but usually amino acids have relatively large non-polar groups, or you have a relatively large surface area as well, so it can form favorable dispersion forces. Okay, but really depends. Yeah, so some of them might not be very soluble in organic solvents, some more soluble. Yeah, so in most cases, they tend to be more soluble in water molecules. Yeah, so in that case, you expect them to be highly water soluble, and that explains why most of them ends up as the building blocks of our proteins. Okay, so over here you have some information given to you about 20 naturally occurring alpha amino acids. So their names can be represented either by one letter or three letter abbreviations shown in the table. Okay, so the table is shown in the next 2 pages. Please take note that these 2 pages are not meant for you to memorize. Okay, so you do not need to memorize the R group of all this. Okay, it's not in your syllabus. Okay, so do take note of it. If I need to explain, then maybe I should just explain some aspect of the tables for you to take note of, and what you can what you can be expected to understand from the table. Okay, so the first thing is Pi is what we call isoelectric point. So this is not in your syllabus, so I think I'll just ignore that. Okay, now what exactly do we mean by the pKa of the alpha carboxylic acid and the alpha ammonium, right? Okay, so what we are talking about is essentially these 2 groups. So this is known as the alpha carboxylic acids, okay, and the other portion is known as the alpha ammonium. Okay, as you know, if this is shown here as the carboxylate salt, but if it is the carboxylic acid, obviously it will have a lower pKa, which is 2.34, as compared to the ammonium, which is 9.69. Remember that ammonium is the conjugate acid of the amine, so obviously it is also acidic in nature. Yeah, you might be wondering why the carboxylic acid is significantly more acidic as compared to ethanoic acid, which has a pK of about 4.76. Well, I mean, if you take note of this, this is a highly electron withdrawing group. Yeah, because at a lower pH, it is positively charged. Yeah, so the ammonium group being positively charged will exert an even stronger electron withdrawing inductive effects, okay, onto the carboxylic acid, and further help to stabilize the carboxylate anion. Yeah, so that explains why for amino acids, the pKa of the carboxylic acid tends to be significantly lower than that of ethanoic acids. Okay, and you can just look through the whole list to understand why. Yeah, and then there's a label here which you may or may not understand. Why did they say neutral? The neutral here do not refer to pHs, they refer to whether the side chain is acidic or alkaline. Okay, so neutral here means that the side chain, right, cannot ionize. Yeah, so for alanine, your side chain is a methyl group. For asparagine is an amide. Cysteine is a CH2SH, a thiol group, and then blah blah blah. Okay, so basically these side chains are neutral, they cannot be ionized. Yeah, so if you're interested, you can just go through the list. You might be interested to know that glycine is the only amino acid that does not have a chiral carbon. And I think you can explain to me why. Okay, yeah. So I'm just going to move on. Again, it's not that I don't want to go through, but really there isn't a point. If you're interested, you can just go through them on your own to admire the different R group. Okay, but I thought what is more important is I need to move on to the part where we are going to discuss acidic amino acids. Yeah, so there are two naturally occurring acidic amino acids: aspartic acid and glutamic acids. Okay, so aspartic acid has a shorter side chain. Glutamic acid has a longer side chain. Yeah, so you notice that over here, right? They wrote here the pKa of the side chain. Yeah, so the side chain here refers to this particular side chain. Let's see. Yeah, this particular side chain. Okay, so you notice that the carboxylic acid group here, okay, of the side chain, right? The pK is higher than the alpha carboxylic acid. Do you notice? You see, the pK is higher than the alpha carboxylic acid. Yeah. Why is that the case? Okay, so I'm going to use a little bit of space here to explain why that is the case. Okay, now, basically, if you really want to compare, maybe I'll just draw a carbon here, okay, and a carboxylic acid, CO2H, okay, and then I'm going to draw H here, and then I'm going to draw in the protonated form of the amino group in the most acidic solution. Okay, and then I'm just going to draw the side chain. The side chain I'm going to draw in maybe yellow. Okay, so I have a CH2 and then a CO2H. Okay, so people, let me ask you a question. Based on inductive withdrawing effect, right? Do I expect the blue carboxylic acid group to be more acidic or the yellow one? Okay, so we can just try it. Okay, so if I'm going to deprotonate this, right, with a minus charge, right? Okay, the inductive withdrawing effect, right, is distance dependent, remember that. Okay, and it is inductively withdrawn by the ammonium group. So you can see that when the carboxylic acid group is bonded to the alpha carbon, right? Okay, the carboxylic species is 2 bonds away from the inductively withdrawing ammonium group. So this is 2 positions away or 2 bonds away. Yeah. What about, let's say, if I'm going to remove the other H. Okay, so let's say I'm going to remove this particular H, and then I'm going to generate this negative charge over here. Okay, it is now 3 bonds away. Did you notice? Yeah, so the inductive withdrawing effect is more prominent on the carboxylic acid directly bonded to the alpha carbon. So it will help to stabilize the carboxylate salts more. And that explains why the side chain carboxylic acid group is always less, the pK is always, or rather the Ka is always lesser, and the pK is always greater than that of the alpha carboxylic acids. Okay, then what about basic amino acids? So there are 3: arginine, histidine, and lysine. Yeah, so in our case here, the side chain over here, right, is basic in nature. Okay, it's basic in nature over here. And you can also see it from the values. Okay, the pKa values. Okay, so I will leave it to you to go and explore. Okay, to go and explore why is it that the pKa value of arginine. Okay, maybe we focus on just arginine and lysine. Why is it that arginine and lysine, right, their pKa is greater than that of the alpha amino group, which is 9.04 and 8.95 respectively. Yeah, I think at your level, you might not be able to explain why the pKa of histidine is 6, whereas the amino group is 9.17. Yeah, so if we ever deal with that question, then I will explain to you during our revision. But over here, I will not attempt to explain to you. So if you are interested, you can go and maybe read up on your own, or you can go and think about it and then ask me during tutorials. Okay, yep. So I'm going to move on to the next section 6.3, the acid-base behavior, which is an application example. Okay, so if I have both acidic and basic group, I will be able to undergo acid-base neutralization reaction stepwise. So at low pH, you expect the amino group to be protonated. And then as I increase the pH, you will notice that the carboxylic acid group will deprotonate first, because it has a lower pKa as compared to the ammonium group. And then this is followed by the ammonium group deprotonating. Yeah. If I ask you to calculate the total charge, so at low pH, in our case here, the charge is +1, provided R is neutral. I think this is very important. And then at the zwitterionic species, then the charge is 0. At high pH, the charge is -1. Okay, the overall charge, I mean. Yep, so the isoelectric pH is the pH where the sum of all amino acid species is equal to 0. Yeah, so largely you have the zwitterions present. Okay, yeah, so I'm going to move on. Let's see. Okay, so I have an isoelectric point here. You notice that for alanine, being a neutral amino acid, the isoelectric point is very close to 7. Yeah, but for lysine, being an amino acid with a basic side chain, right? The isoelectric point is 9.74, which is greater than the amino acid with the neutral side chain, or greater than 7. Yeah. Then if I have an acidic side chain like aspartic acid, you would expect the isoelectric point to be way below 7. That's 2.77. Okay, yeah. So if you want me to explain to you why, I think we can I can explain to you using exercise 6.1. I think that would be easier for me to explain. Okay, so we are looking at let's see, what are we looking at? We are looking at lysine. Okay, so I'm going to draw the skeletal structure of lysine out. Yeah, so maybe it's easier for us to discuss. Okay, so I'm just going to zoom in a bit. Okay, so the skeletal structure of lysine. So again, I have an alpha amino group. Okay, so I'm just going to draw out NH3+, because at the lowest pH it will be protonated. Okay, then I'm going to draw out the carboxylic acid. Okay, which is the carboxylic acids, OH. Okay, and then I'm going to draw out the side chain. Okay, the side chain contains 4 CH2s. Okay, so that would be 1, 2, 3, and 4. Okay, and then I'm going to get the protonated ammonium group as well. Okay, so this will be the species at very low pH. Okay, yeah. So as I increase my pH, what is going to happen? So as I increase my pH, I think earlier on we do agree, and we agreed that the carboxylic acid, definitely it will be the one having the lowest pKa. Okay, so as I increase my pH, okay, what I'm going to get is I'm going to get a carboxylic acid being deprotonated. Okay, so the rest of the species, I'll just draw them out as the ammonium cations. Okay, or rather ammonium ions. Okay, and then this NH3 plus. And then I'm going to draw out the carboxylate salt. Okay, CO2 minus. Okay, and then as I continue to increase the pH, okay, so what's going to happen is that now I have to decide whether this ammonium get deprotonated or the other ammonium gets deprotonated. Okay, how do we understand which one gets deprotonated? Yeah, so we can understand this from two different perspectives. Okay, so the first perspective we are looking at is the distance the ammonium group is away from the carboxylate anionic group. Okay, now because the carboxylate anionic group will exert an inductive withdrawing effects, okay, on the protonated amino group. Yeah, so the closer it is to the carboxylate group, right? Yeah, the more destabilized it will be. So imagine that the protonated amino group is already positively charged, if I have an electron withdrawing group that withdraw electron density away from the positively charged center, right, it will destabilize it. Yeah, so if you compare between the two, right, I think it is not difficult for you to conclude that this is the stronger acid. So it will be deprotonated first. Okay, so that is one perspective. I'm going to explain to you the other perspective later on, so please bear with me. I'm going to just draw this out first. 1, 2, 3, 4. Okay, so NH2 and then CO minus. Okay, another perspective which you can look at is the availability of these lone pairs of electrons to grab back the H plus. Okay, so if I draw the carboxyl, if I draw this species as the one as opposed, okay, as opposed to the other one, maybe I'll just draw the other one out in red. Okay, so let's say you predicted wrongly lah. Okay, let's say you predicted wrongly. You went to draw this out. Okay, so I'm going to ask you a question. Between the blue and the red structure, which is a stronger base? Yeah. Okay, so which is a stronger base? So I think you can predict that the red structure is a stronger base. Yeah, because in terms of the relative distance away from the withdrawing carboxylate group, right, it is further away. Okay, as compared to this. Yeah, so if this is a stronger base, then I would expect the protonation to occur here instead of here. Yeah, so therefore the species I've drawn in red is not a reasonable species. Yeah, because it is likely to allow the H plus to swap in position between the amino group and the ammonium group. Okay, or you can say the alpha ammonium group and the gamma ammonium group. Yeah, okay, so with that then I think you are able to understand the two different perspectives. I'm just going to erase this portion. Okay, and then I'm just going to draw the final species out at very high pH. This is straightforward. I'm just going to draw the lone pairs for your information. Okay, and then the carboxylates. Okay, so these are the 4 species at the various pHs lah. I mean, do take note that at any pH, all the 4 species exist together. Okay, do take note of this. Yeah, the only difference is that it exists in different amounts. So some species exist predominantly at a certain pH. Yeah, so for very low pH, of course, I expect this to be the dominating species. And then if I increase the pH to about 3-ish, this should be the dominating species. Okay, yeah. So next, I thought I just want to do a little extension, just a very short one, not really extension, but it's also to allow us to identify the major species at the isoelectric point. So first, let us calculate the total charges or the total charge of the various species. The first one is plus 2. Okay, sorry, yeah, it's not working so well. Okay, so the first one is plus 2. Okay, the middle one is plus 1, and then this is 0, and then this is minus 1. So I expect that at the isoelectric points, this will be the major species. Yeah, because this is a zwitterion. And I think you can also explain why the isoelectric point is likely to be above 7. Okay, like in the case of lysine, it's like 9.74, right? How are we gonna understand why? Okay, we can just go back to this list. Did you notice that the pK of the carboxylic acid is 2.18, and then if I increase it further, the alpha amino group will get deprotonated. That will be 8.95, right? So 8.95, the majority of the species at 8.95 will actually be these two. Okay, so it will be wait, let me just, oops, sorry, the one is missing. This is plus 1. Okay, okay, so I'm just going to write down the pKa. Yeah? So pKa, let's see, pKa 2.18 equals to 2.18. Okay, and then the next one is pKa is equals to 8.95, and then pKa is equals to 10.53. Okay, now if I'm going to predict the major species at the relevant pHs, so let's say at pH 2.18, the major species will be both this and this. Why is that the case? Because remember, that is the maximum buffer capacity. Okay, so I should have equivalent amounts of the acids and the salts. So this is the acid, this is the salt. Okay, so at 8.95 pH, the major species will be this and this. So it will also include the zwitterion. Okay, then at 10.53, I will have both this and this. Okay, equivalent amounts. Yeah, then how are we going to predict the zwitterionic point? So basically the isoelectric point. What am I talking about? The isoelectric point. So the isoelectric point basically is like the halfway mark between pKa 8.95 and pKa 10.53. Yeah, so if you sum the two up and divide by 2, you should get about 9.74. Yeah, so that is a proxy you can use to calculate the isoelectric point. However, you're not required to know. If you're ever asked, you'll be guided in an assessment. Okay. Yeah, but I'm just using this as a little extension to explain to you how the isoelectric point can be calculated, and how can we obtain the major zwitterion species. Okay, or rather how can we predict the zwitterionic species by simply just summing up the relevant charges in the species. Okay, yep. Next is an application example for titration. This will be very similar to the one you learned under acid-base equilibrium, so I don't think I'm going to discuss too much. So for example, in lysine, pKa1 2.34, pKa2 9.60. So pKa1 is due to the carboxylic acid, pKa2 is due to the protonated ammonium. Okay, yeah. So I think over here they are explaining to you at a pH lower than 2.34, the majority of the species is the +1 species, and then at a pH between 2.34 and 9.6, I'm probably going to have quite a bit of the zwitterions, which has a total charge of 0, and then pH above 9.6, I'm going to have the negatively charged anion. Okay, yeah. We can also have a titration curve. Okay, so this is very similar to a diprotic acid. Yeah, so I don't think I will go a lot into details, but I think I have also earlier on explained to you how do you actually predict the isoelectric point, how do you predict the major species, and when pH equals to pKa, what are the major species present. So I have already used exercise 6.1 as a place to kickstart your understanding towards this, which is a simpler example. The glycine use is a simpler example. Okay, so yep, so 2.34, I'm going to expect both this species and this particular species. Okay, and then the isoelectric point, which is very near the first equivalence point. Okay, so over here, so I'm going to have essentially the zwitterion, largely the zwitterion, and maybe very little of the +1 and a very little of the -1 species. Okay, and then after that, I'm going to reach here, which is pH equals 9.6. I'm going to have both the zwitterion and this. And then any further increase in pH or any further addition of OH- will cause the pH to shoot up. Alright, so I don't think I need to explain this further. If you have any issues, please go back to acid-base equilibrium lectures. If not, we can discuss during tutorials. Okay, and then for peptide formation, in the human body or in living organism, it is a little bit different from the laboratory system. So in the living body, you can actually use a carboxylic acid and an amino group and react them together, but they don't react directly. Yeah, so there is catalyst involved, which I will not go into detail, and in the process, it will lead to the formation of a peptide bond. Yeah, so do remember that for this particular portion, right, we are not saying that the carboxylic acid and the amino group react directly. Yeah, because when they react directly, it will be acid-base reaction instead of condensation. Yeah, but in our case here, this particular reaction is aided by the presence of enzymes. So in that case, we are able to allow the condensation reaction to take place at the ambient condition in the body lah. Okay, so a dipeptide is formed when two amino acid comes together and releases a water molecule. Okay, so this is the terminology you need to be familiar with. Okay, and one water molecules. Tripeptide is formed when three amino acids come together to release two water molecules. In case you're wondering why dipeptide only releases one, well, that's because the condensation reaction between two amino acids only occurs at one of the carboxylic acid group and one of the amino group. Yeah, so that explains why it only releases one water molecules. Okay, so over here we have exercise 6.2. Okay, where we are required to calculate the MR of the small peptide X, which is being hydrolyzed according to the following reaction. Yeah, so when X is hydrolyzed, I get two equivalent of this particular amino acid with MR 75, one equivalent of this amino acid with MR 89, and two equivalent of this amino acid with MR 115. So all in all, we get 3 amino acid after the reaction. Okay, so that means that the number of water molecules that is required to react with X, it will be 4. Okay, why? Okay, so you can think of it this way lah. If a dipeptide were to undergo hydrolysis, you cannot simply just sum up the MR of the amino acid without adding the MR of the additional water molecules, right? Yeah, so it's the same story. Yeah, so in order for us to calculate the MR of X, right, we need to sum up the amino acid MR. So in this case, 75 times 2 plus 89, okay, plus 109 times 2. And we need to subtract off the number of water molecules being released, okay, in the course of the reaction. Yeah. Okay, so okay, why is it being released? Okay, so imagine that these 5, they are combining to form amino acids. Yeah, so in the course of reaction, they will be releasing water molecules, right? Yeah, how many water molecules do they release? Is it 4 or is it 5? So I think we have to understand it as 4. Yeah, so therefore, right, the MR of X cannot simply be the summation of the MR of all the amino acids. So we have to subtract off 4 water molecules, which is 4 multiplied by 18. Okay, yep, okay, so I think there's a typo here. This is just 105 times 2. Okay, so with that, if I punch my calculator, I will be getting 377. Okay, so please check your answers before moving on to the next portion. Right? Okay, so over here, peptides made from condensation of up to 50 amino acids are called polypeptides. Okay, anything larger we can classify as proteins. Okay, again, I do not need to, or we do not need to go into details on the nitty-gritties of the reaction, but do remember what I said earlier on. They do not simply just react the carboxylic acid and the amines. Okay, the presence of enzymes allow the condensation reaction to take place. Yeah, please remember this extremely important facts. Okay, next we have exercise 6.3. We are asked to draw the structure formula of a dipeptide with the sequence ASN LYS. Okay, show the ionic form which will exist at pH 3. Okay, so earlier on, I think there's one little thing which we didn't highlight. When amino acids combine, right, the peptide sequence, right, is often written from the N, this is called the N terminal, to the C terminal. So this is the C terminal. Yeah, you cannot reverse it. Okay, yeah, so this is very important. You don't reverse the order just like that. Yeah, so in our case here, when it's ASN LYS, right, so when they react, yeah, it is definitely this carboxylic acid react with this NH2, not the other way around. Yeah, so in this case, when we are drawing the species, because it's at pH 3, right? So I'm going to expect this particular ammonium amino group to be protonated, okay, with a C and a H, okay, and then the side chain, I will simply just write it as CH2, okay, as the amide, right, okay, and then NH2, okay, and this portion is the special one, not special, I mean, it forms the amide, right, so I'm just going to write it in blue, okay, and then NH, okay, I'm just going to continue to write the rest in red, okay, and then C, with a H here, with a CO2H, remember, is pH 3, so it's likely to be protonated, okay, and then of course the side chain, in our case here, the amino group will be protonated as well, okay, yeah, okay, just going to write out the amino group, so NH3+. Some of you might be asking, how come this group is not protonated? Because these are amides. Yeah, so remember that amides, the lone pairs of electrons is partially delocalized over the carbonyl oxygen, so it should not be protonated. Okay, because essentially it's neutral. And why is it not hydrolyzed? Why is the amide linkage still there? Well, I mean, they didn't say that the temperature is being increased, right? Yeah, so it will just remain as it is. Okay. Then the next portion is on proteins. In the old curriculum, proteins, there's a huge portion of it dedicated to the notes or to the syllabus. But for the new curriculum, proteins, the large part of it is not being highlighted or it's not being replicated in the new curriculum. Yeah, so there isn't really much for us to discuss. The biology students, do feel free to share what you know to your non-biology friends. Because I think proteins itself is quite an interesting topic. Yeah, but by and large, there are different kinds of proteins, structural and catalytic ones, which are called enzymes. I think you learned before in secondary school. The structural ones provides the structural makeup of a living organism. So for example, keratin is the protein of hair, nails, horns, etc. Okay, hydrolysis of proteins is something we need to be familiar with. Okay, so it's important for you to recognize the condition. You need to heat it under reflux in the presence of mineral acids or alkali several hours in the lab. The several hours is important. Okay, if you don't wish to do it in several hours, then you better find a good enzyme which can selectively cleave certain bonds. Okay, so either use an enzyme and perform it under ambient condition, which cleaves specific bonds. Yeah, so I think you have to be a bit careful. Usually enzymes only cleave specific bonds. Yeah, but if you want to cleave all the amide linkages or all the peptide linkages, then you have to use a mineral acid or a mineral base. Okay, so to reflux the system for several hours so that all the amide linkages can be overcome. Okay, yeah. So with that, this is the only thing which I think you need to be familiar with. So do remember the not exact lah, but the conditions you need lah. Yeah. So reflux, mineral acid or alkaline, several hours. Okay, or choose an appropriate enzyme which cleave appropriate peptide linkages. Okay, not all the peptide linkage can be cleaved by all enzymes. Remember from what you learned in secondary school, right? Enzyme is substrate specific. Yeah, so it does not cleave all peptide bonds. Okay, next we have exercise 7.1. We have aspartame is the name of the artificial sweetener used as a sugar substitute in many foods and beverages. Draw the structure formula of all the organic products obtained when aspartame is heated with dilute sulfuric acid. Okay, so first of all, we need to understand the different functional groups. So over here we have amides. Okay, so amide will be hydrolyzed. Okay, next we have an ester. So an ester will be hydrolyzed as well. I think that's about it. Okay, we need to check out the reagent, which is sulfuric acid. So the hydrolysis product should be protonated. Okay, so with that, I'm just going to draw in the answer. So the top portion, okay, this portion I'm just going to draw in. So I'm going to get the carboxylic acid group out, and then the protonated ammonium group. Okay, and then after that, the other carboxylic acid will just remain intact. Okay, and then of course this portion I'm going to end up with methanol, CH3OH, and then of course the remaining parts, so this is the remaining parts which I need to draw out. So yeah, so that will be the carboxylic acids, okay, and NH3 plus, remember you need to have the plus, okay, and the phenyl ring. Okay, I think this portion I need to draw it slightly clear. Okay, like that. Okay, yep, so that will be the answer. Remember that please check that all the basic group is protonated. Okay, so this is quite often being tested. Okay, and I think they ask for organic products. Okay, so along the way you might just want to incorporate the counter anion out somewhere. So maybe I can just draw a sulfate somewhere because they want the products. Yeah, so the product is likely to be the ammonium, or rather the salts of the sulfate salts, okay, of the amino group of the primary amine, you want to put it. Okay, yeah. So finally we have a summary of reactions of amines and amides. Yeah, I think this is something which you can do on your own, but because nitrogen compound is a relatively new topic, so I will just run you through the summary. Okay, so the first thing is the first reaction we are experiencing here, right? When we are converting bromoethane to ethylamine, right? Essentially is nucleophilic substitution. Okay, so in this case, we need excess ethanolic ammonia. Okay, probably we can incorporate concentrated ammonia and then heat in silk tube. Okay, so this particular reaction is a nucleophilic substitution. We need excess ammonia because you want to ensure that you do not end up with the quaternary ammonium salts. Okay, and then of course the second reaction, which is something we learned in halogen derivatives, so it's ethanolic KCN. Okay, ethanolic KCN heats. And then you perform nucleophilic substitution, and then after that you perform a reduction using lithium aluminium hydrides in dry ether. The difference between the two products is that one is a step-up reaction containing 3 carbon, the other one is simply having 2 carbon. Yeah, so that explains why is it that one you use ammonia, the other one you need to subject it to ethanolic KCN before reduction. So that's the difference. Okay, and then after that you will perform hydrolysis. Okay, after hydrolysis you will end up with propanoic acid. So this is simply H2SO4 heat. Okay, and then after that the carboxylic acid and propylamine, right, will undergo acid-base neutralization reaction. So I will end up with carboxylate anion, and of course the relevant ammonium cation. Okay, so with 3 with 3 carbon, 1, 2, 3. Okay, then after that I will convert my carboxylic acids to the acyl chlorides. Okay, using PCl5. If you want to use, you can use thionyl chloride. It's really up to you. As I said, all road will lead to Rome. Okay, and then phenylamine will react with it, okay, to give us the amides. Okay, so I'm going to get the amide from here, and H, and then CO, and then CH2, CH3. Okay, and then how do I obtain phenylamine from nitrobenzene? Remember the special reaction. So first we need tin in excess corn hydrochloric acids, and then we need to heat it, and then this is followed by adding sodium hydroxide to generate phenylamine. And then with bromine, the amino group being 2,4 directing, and it's a very strong electron donating group due to the lone pairs of electrons partially delocalized into the phenyl ring. Do expect tribromination. Okay, and then of course sodium hydroxide heat under reflux. We are going to expect the amide linkage to be cleaved. So when the amide linkage is being cleaved in the basic condition, I will end up with phenylamine. And of course, the carboxylic acid will not be a carboxylic acid, but it will be a carboxylate salt with the corresponding counter cation. Okay, so I hope this particular summary allows you to see the reactions of amines and amides. And we have also incorporated cyclic or rather aromatic amines here for your information. Yeah, and this is quite a unique reaction. So we are just hoping that you are able to remember the reagents and conditions for now. Okay, so with that, we have come to the end of organic chemistry. Okay, we end off the topic with a summary of oxidizing and reducing agents. Okay, so you might want to just take note of some of the information given here. Again, it's not meant for you to memorize, but rather is for you to look through and then understand some of the chemistry involved and not to get confused between why is it that one topic we are using that, the other topic we are using something else. Yeah, and also to be a bit careful when you are using potassium permanganate, because do take note that potassium permanganate can oxidize many things, such as it can perform section oxidation for substituted or for alkyl benzene. It can perform oxidative cleavage for CC double bond in alkenes. It can oxidize primary and secondary alcohols. It can also oxidize aldehydes. Yeah, so if you want a reaction to be quite selective, then make sure you choose the correct reagents. Okay, so with that, we have come to the end of organic chemistry. For the rest of the topics we're going to discuss, it will be largely physical chem topics and inorganic chemistry topics. So we're going to end with our H2 curriculum with transition metal chemistry, which is a very interesting topic. Yeah, so at this point in time, you might want to review all the concepts you have learned in organic chemistry from topic 8 onwards, and where possible, you can create a mind map, or in the future I'm going to come up with a video to maybe showcase to you how you can go about revising for organic chemistry. Yeah, so with that, I thank you for your attention, and do look out for future videos on topics beyond organic chem. Okay, so yeah, have a good rest.